Hello, Chemistry 10HH students. This is Mrs. Altman. We are on video number 39, Gases, Parts 5. Here are our objectives for today's video. Pause here. So thus far, we talked about a number of laws: the ideal gas law, Dalton's law of partial pressures, Charles's law, Boyle's law, Avogadro's law, all of which are well and good and have a lot of applications in a lab setting. But it is also important to understand the reason why gases behave the way that they behave, and that is where kinetic molecular theory comes into play. I'm going to also call this KMT. So KMT describes the properties of an ideal gas and why the ideal gas law works. And it's going to be broken up into different postulates. Pause here. So the first postulate is that gas particles are so small that the volume occupied by the molecule itself is negligible, meaning that the volume of gas is actually the space between the particles. So what this tells me is that smaller gas molecules will be more ideal than larger gas molecules. So a common misconception that I see with students is they'll ask me what gases are ideal and what gases are not ideal. And I understand why students ask the question. There's no particular gas that is ideal or is not ideal. Some are just closer to being ideal and less close to being ideal. And what I mean by ideal is I mean that we can perfectly describe the behavior using PV equals nRT. And something that is not ideal, you'll see that in an experimental setting, PV equals nRT will not quite work. So what we get from KMT postulate number 1 is that smaller gas molecules follow PV equals nRT with a higher degree of precision. So like helium is going to follow PV equals nRT a little bit more perfectly than, say, radon. Pause here. So the second postulate, gas particles are in constant motion, which makes sense. Everything is in constant motion. And then the collisions of the walls of the container create pressure. One of the sort of applications that we see of this is that when we are at higher temperatures, meaning we have more motion, we will have a gas that behaves in a little bit more of an ideal way. Pause here. So the third postulate, we haven't talked too much yet about intermolecular forces. We're going to talk way more about this in a later chapter. I will let you know right now that H2O just has very, very high intermolecular forces. If you didn't already remember that from biology, that will just make your life a little bit easier to remember it. So for an ideal gas, there are no attractive or repulsive forces between gas particles. What that means is they will bounce off one another if they hit one another, and they'll have what's called a perfectly elastic collision, meaning that no energy is lost in the process. And when I say lost, I mean given out to the surroundings. You never have a total loss of energy. So what this means is that things that have low intermolecular forces, so helium, for example, has very low intermolecular forces, will behave in a more ideal way than something with high intermolecular forces, say H2O. Pause here. The fourth point, so the average kinetic energy, if you didn't already know what kinetic energy is, it is just 1/2 mv squared. Where m is going to be mass and v is equal to velocity. The average kinetic energy is directly related to Kelvin temperature. So what this explains to me is why larger particles, like heavier particles at the same temperature, are going to be moving slower than lighter particles. So let's just say I've got a sample of helium on, let's say, a container on the left, and then on the right, I've got a sample of radon. They are both at the same temperature, just because I told you they were the same temperature. There's no other way for you to know that. Because they're at the same temperature, that means that the helium must be moving faster and the radon must be moving slower. What I see is that there is an indirect relationship between mass and then the squared velocity. Velocity is just really speed in a direction. More on that when you take physics. But for right now, you can think of it as just speed. Pause here. And then this is just in a little bit more detail what I just said. So temperature is a measure of the average kinetic energy of the gas particles. you will actually see that there are some gas molecules that are very, very slow moving and some that are very, very fast moving, which is the same reason why you can see evaporation at room temperature. You don't need to be at the boiling point for something to evaporate. And that's because we have this distribution of temperatures. This is also another explanation for why we use Kelvin and not Celsius. So some of you have probably thought that that seemed a little silly, and that's not wrong to think that, but Celsius can be negative, whereas Kelvin cannot be. And we can only have this relationship that is direct between temperature and kinetic energy when we use a scalar quantity like Kelvin temperature that cannot be negative. Pause here. So this is just a consequence of the equation on the last page. So you've probably heard of the terms diffusion and effusion before. Diffusion is the rate at which a gas disperses. So if I open a container, how quickly does it move? And then effusion is just the rate at which gas moves through a small hole, so like a pinhole. And then we can relate the rates and the molar mass of a gas. Conceptually, what you should think to yourself is that heavy molecules are going to travel slower, which logically makes sense. And this just mathematically gives a relationship between the two of them. We're going to spend more of our time conceptually on this, but we will do some math practice in class. I just didn't want to include it in this video because I really wanted to focus on the concepts in this video. Right, that is all for today's video. Thank you so much for watching and have a great night.